So welcome everyone to the first of our autumn series of Europlanet Society webinars. We will just give it a couple of minutes for people to join us. It was quite short notice putting this one together, so thank you very much for those of you who've joined us today. We will be starting with a presentation by Ingo about the aerial data challenges, and then we'll be hearing from Nick, Giacomo and Javier and Dan about the Explore Lunar data challenges. If you have questions, then pop them in the Q&A or in the chat. But as I say, we'll just give it a couple of minutes for people to finish their lunches and get on and join us today. I feel that I should be like Neve in the morning briefings and ask everybody what the weather is like. Ingo, what's it like with you?
Yeah, pretty much. And should I start sharing my screen perhaps?
Yeah, that's probably a good idea.
Okay. There you go.
Okay, so we probably should get started. Thank you very much everybody for joining us today, and thank you to our speakers too for agreeing to participate in this first of the Europlanet Society autumn webinars. Today we're going to be talking about data challenges. So first of all, we're going to be hearing from Ingo Waldmann about the aerial machine learning data challenge, which has been running now for 3 years and has been extremely successful. And then we're going to hear from the Explore team about the Explore Lunar data challenges, which have just launched this September. And then we're going to have a bit of a conversation about data challenges, how they can help in dissemination and bringing in new communities, and what are some of the things to think about in putting a data challenge together, what are some of the issues, and what are some of the benefits that, that have come out of that. So I'm going to hand over to Ingo, and Ingo, take it away.
Well, yeah, thanks very much, and thanks very much for the opportunity to give us a brief overview. So this is, as Anita very nicely introduced, the Aerial Data Challenge, which is part of the Aerial Space Mission Consortium. So Aerial is launching in 2029, and the idea is that, you know, to do next generation science with atmospheric modeling of many extrasolar planets, this is what Aerial will look at. We really need to up our game in terms of, you know, the machine learning and the statistics that we're using at the moment, because it is a big data mission in the end. So machine learning in exoplanets has, you know, ramped up very, very rapidly since, say, 2018-19. Before that, there was hardly anything, and now it's an exponential increase in papers, which is great, but, you know, very much reflected in other sciences and industry as well. And what we usually see is that machine learning is happening in fields where there's plenty of data, such as transit surveys, but also in the modeling of atmospheric transmission spectra and emission spectra, which is something that, you know, we're interested in. There's a obviously very natural synergy between the AI community, sort of the fundamental machine learning community, and astronomy. We have the very hard problems in the big data sets. I mean, planetary science has enormous data sets with super high quality. And the machine learning community has all the good detrending tools, but those two communities don't necessarily interact very well with each other. And part of that is, you know, a lack of familiarity, but also, you know, different nomenclature and different ways of, you know, working. And so there's always been a bit of a disconnect. And we thought, you know, one of the ways of, you know, bridging that and bringing this machine learning expertise into our field, in my case, exoplanets, we should, you know, try and run some data challenges. The idea there is that you package up a small bit of your larger problem in an understandable format, that can be solved within a couple of months, for example, or at least attempted. And that, piecemeal is easier to digest for people outside the community. It's an easy way in. And that hopefully leads to more collaborations, for example, later on after the data challenge. So we've started in 2019 at the European Conference for Machine Learning at Würzburg. Then 2020, COVID happened, and everyone had different things on their minds. So we skipped that, and then we did another one, 2021, which is online, and this year we've upped our game a bit and went for the big conference, which is Europe's, which is the international biggest machine learning conference in 2022. Yeah, so I'll talk about this later potentially. Proposal writing, and it's actually trying to organize an entire big workshop, and the World Data Challenge, the organizational components are quite hefty at times, but I think it's worth it. For example, in the last year's challenge, we were the biggest challenge of that ECML conference in the last 3 years. Attracted around 140 machine learning teams and individual people. And what we didn't anticipate is that the outreach impact it had. And 3 universities used our data challenge as their MSc thesis project in computer science. So 2 universities in Germany and 1 in China, so Nodjumi University. So that was very good, and our workshop was very well attended with around 50 people. So these quickly become sort of mini conferences, which is very good. And in the 2019 challenge, we had our youngest participant was 14, who ranked in the top 5 actually. So he's a bit of a boy genius, and it's quite sweet because after that he decided to go on have a career in machine learning and astronomy. So that's nice. And last year as well, we randomly, we did a little press release, but not thought much of it at the end of the machine learning challenge, and ended up in the Portuguese popular culture, because the winner was Luís Simões, and he's from Portugal, and he was frontline news in Portugal for a couple of days, and even featured as the hardest, as the hardest question on their game show Joker, which is sort of like Who Wants to Be a Millionaire. So that was quite unexpected, but this is a different angle to what we expected. We thought it's important for the scientists to communicate, but actually it has a much bigger reach, and people outside the traditional sciences, or also in the industry, can really participate and help with our scientific problems. So Luís, for example, comes from industry, so he has a startup in Portugal. So what can we do this year? So this year we are looking at trying to model the atmospheric parameters of an exoplanet with machine learning. The problem there is that with a traditional method, which is Markov chain Monte Carlo, and this is sampling, the parameter spaces are becoming too big, and we can't really model this anymore in a classical way. There have been quite a few approaches so far. So this is a sort of burgeoning cottage industry of doing machine learning and trying to solve the inverse problem of, what do we actually learn out of a atmospheric spectrum? What can we derive from that? But it's very much burgeoning, and there's much room for improvement. So we thought a machine learning challenge will be useful, especially also that the inverse problem is one of the hardest problems to solve in contemporary machine learning. So, especially doing it in a Bayesian setting is very, very difficult, and it's not really been fully solved anywhere. So there's a broad overlap between our problem of to interpret atmospheres of extrasolar planets to other fields, for example, in biochemistry or medicine, where they try to identify cancer in scans, for example. It's the exact same thing, statistically speaking. So we built a gigantic data set for people to use and train on and build their models on. There's 100,000 atmospheric models and 26,000 full Bayesian retrievals. So, doing the MC. So we used 50 million CPU hours. So if you'd be running this on your own laptop, you'd be starting at the time of Galileo's birth. So that's relatively long, but we thought, it's a good data set to actually leave for the community as for example, lookup table, or as a benchmark data set for further AI development in inverse modeling. And so the SciML group, which is part of the STFC at the UK, is actually now curating our data set, which is very nice, as a machine learning data set. What we found from the previous challenges is that a lot of the interest comes from the machine learning community, because they do want to model something that makes sense and something that is actually important in a given setting. So people are very, very bored of modeling celebrity faces and cat pictures. So this is part of the reason why, actually machine learning in science finds quite a broad appeal in our community. So this year's track is competition has two tracks, a light track and the regular track. And the light track is where you basically just identify the mean and the error bar of a parameter such as abundance of water or temperature. And the regular track is you get a full posterior surrogate posterior distributions of your machine learning retrieved inverse model. These tracks have prizes attached to them, and with NeurIPS, with ECML, the prizes are usually around a sort of a €500 note. In NeurIPS, the prizes are quite often around the $25,000 to $50,000 note. We obviously can't afford that, so we pushed our boat and came up with a sort of 1,000 and 2,000 for the two individual tracks, which still attracted a lot of people. So we're one of the biggest competitions at the conference now, with over 220 participants. We've got quite a few sponsoring partners this year, and we've just signed up another industry sponsor yesterday, Saturn Cloud. So it's getting to the right people, and it's putting out the right message. And as at some point, this becomes self-propagating almost, which is nice to see. And as I said, these techniques are generally applicable, and I think this is also where the appeal is. If you can showcase that you're not only doing your tiny little science here, but that the technique to do your tiny little science can be applied more broadly to society, then you're also increasing the appeal of your data challenge. So we're nearly done with the data challenge. In fact, in 5 days. 6 days, but please do have a look at the website. There's loads of material, loads of background blog posts. We wrote 2 papers for the data set and the baseline model and so on and so forth. So it's quite a nicely written website. Do have a look, and ultimately it's just an excuse to go to New Orleans. So thank you very much, and that is my presentation done.
Thank you, Ingo. Just while we hand over to Nick and to the Explore team, if anybody's got any questions for Ingo, we'll come back and we'll have a discussion time towards the end. But if there are any questions now, then drop them in the chat or in the Q&A. But otherwise, Nick, we'll hand over to you. We are a select group today, but don't worry, we will be recording, or we are recording this at the moment, and we will be putting the recording online, and it will be available on our YouTube channel afterwards. So, Nick, I will hand over to you in that case.
All right. Thanks very much, Anita, for giving me the floor. So I will quickly, before talking about or letting the others talk about the Explore Data Challenge, I will briefly tell you what is Explore, so we get a bit of the context of the data challenge. So basically, Explore is a European project which is aimed at creating new lunar exploration and Gaia science applications that will be mainly powered with new visualization and machine learning features. And those will be deployed on different science platforms that exist in Europe and elsewhere. And so we try to make the connection between all the science data archives of the different agencies and institutions and connect them with the science archives and the communities to make data exploitation more exciting, faster, better, more useful. And of course, this should all happen in a fair plus open way nowadays in terms of data, code, so the applications and the science. And this is my last slide, just to quickly say the kind of scope we have for our science exploitation. So these cover a broad range of aspects. So we go from galactic science, so understanding the distribution of stars in our galaxy, as well as the interstellar medium in our galaxy. So these are the two first GARC and GTOMO applications. Then we have two applications that provide, let's say, tools for the community to study individual stars or groups of stars. So one is about spectral energy distributions, and the other one is about spectral discovery of stars. So basically trying to figure out which stars look similar to each other in terms of their spectra and their other stellar properties, and which stars look different. So we're finding anomalies, interesting cases, and stuff like that. And then the last two applications that fit most with Europlanet, of course, are the lunar applications. And these are two. And the first one, LXplo, focuses more on multi-scale data and remote sensing of the moon. So these are orbiters around the moon that take images or spectral cubes, etc. And then the second one is more oriented towards the in situ exploration of the moon. So we're thinking about robots, rovers, and eventually also again humans, of course. And so these are the kind of applications and the context of Explore. And I would like now to give the floor, I think, to Giacomo, who will start and tell you a bit more about what is the actual data challenge and the context of the data challenge, and you will see how it relates to Explore.
Yeah, thank you, Nick.
So I'll stop my presentation.
I will share my screen. Should be this one. Can you all see?
Perfect.
Yeah, so I will start to present this the work that we did, or at least that we're still doing while preparing this data challenge, because it was our first attempt to create a data challenge focused on the moon and in the recognizing of specific feature on a specific region of the moon, while being mostly accessible to not only experts, but also for students and so on. So I will leave this floor to Daniel, which will introduce all the aspects that we defined to create these challenges.
Yeah, so thank you, Giacomo. So I'll talk a bit about why we wanted to actually create any data challenges to start with as part of the Explore project. So we realized that we had quite a lot of high quality data available for the moon. So that's visible imagery, hyperspectral, thermal sort of inertia data, also derived products, so people creating their own elevation models from stereo imagery, things like that. But there were tools for people to be able to process these and sort of combine this data, but not on sort of the large scale that machine learning can help work with. So now that we know that, well, now that we have novel and sort of complex processing tools for using machine learning, we wanted to combine that with lunar exploration and try and merge these, or get these two communities to collaborate more. And also the fact that there's a lot more interest recently in the moon, what with sort of the Artemis missions now, hopefully getting to launch in November, but also the 50th anniversary of the Apollo 17 missions is coming up in December, I think it is. So there's a lot of interest in lunar exploration and also machine learning, and we wanted to help use that to build a community around the Explore SDAs as well, to build this sort of wider community around them, to sort of further this exploitation of space data. But also, and this links a little bit more into some of the outreach elements of the data challenges, but we also want to try and inspire new generations of space scientists, lunar scientists, planetary scientists, and also sort of get people to think about other possible careers in STEAM fields as well. So can you go to the next slide, Giacomo? Brilliant, cheers. So what we actually have is 3 separate challenges. So we've got our main machine learning challenge, which I think Giacomo and Javier will talk about mostly. So this one's mainly geared towards students, university students, researchers, academics, professionals at companies in sort of related areas. So that could be planetary science. So they've got a lot of experience with working with this data manually. But also anyone with expertise in data processing, use machine learning, things like that. So we want to hopefully get a broad spectrum of backgrounds that people come from participating in this challenge. Then we also have our outreach challenges, which are the classroom and public ones. So these are a bunch of sort of hands-on or online challenges in the case of the public one. They were mainly targeted towards sort of the lower secondary school age groups, so sort of 10 to 14 year olds, but they can be performed by anyone. So the classroom challenges are, as you'd imagine, to be performed in schools. But then the public one is a completely online challenge, which you can actually go to the Explore Data Challenges website to take part in. And I think that might be a little bit more information on the next slide, Giacomo. Yeah, so this is about the classroom activities. So the focus for these was to actually teach students how to map real lunar satellite imagery for hazards. So this is things like craters, rills, ridges. And we were doing this by providing some activities to give background information about what machine learning is, why you need to do some mapping beforehand to train your machine learning model to be able to infer on data it hasn't seen. But then also about lunar exploration, because especially at the age groups that we were targeting, it's not something that students had particularly seen a lot of. And you can actually find all of the classroom material online to download at the Explore Data Challenges website, which is just exploredatachallenges.space. So we also have the public lunar challenge, which is focused on similar activities. So they're mostly on the online versions of what you could expect to see in the classroom activity. But the main task is to plot a rover journey across a region of the moon that you can see on the left. And that's, so as you're plotting the region, you also have to pass through all of the experiments that you can see on the left. So it's a fun little task to try and avoid some of the hazards, the restricted zones where you have too high of a gradient for your rover to get across. And if you actually either sort of download the PowerPoint and draw a line on top of it with lines and do your rover traverse that way, or scan in your drawing on top of the image. If you submit that by the 21st of November, you have a chance to win a piece of real moon rock as well. And if I think the QR code, if anyone wants to quickly scan it, does take you to the online portal for the public lunar challenge. But I think the next slide will be about the machine learning challenge activities. So this is like I said, a machine learning challenge to identify specific features. So these are craters and boulders in a particular region of the moon, the Arctic Dome. And you can find all of the relevant information, the materials, the data set on the Explore Data Challenges website. And I think Giacomo and Javier will talk a little bit more about how this challenge was sort of devised.
Yeah, thank you, Dan. So I will just start a brief from the selection of the targets because on the moon, but also in general, the object detection or segmentation tasks or problematics needs to have some targets to be trained by the models. And actually, there are really too many targets that can be used as for the training, like craters, boulders, rills, domes, dikes, pits, and all geological and geomorphological features that can be seen across all the solar system. Actually, most of those features, but we needed something to be kind of easy for all the participants, not only for the expert ones, because we didn't expect that most of the participants to those challenges will come from planetary sciences field of work, but mostly from machine learning or computer sciences. So we needed something that can be also used and interpreted and easily recognizable by those not expert in planetary sciences. And so we needed something that not only had simplicity in their descriptions, but also in their recognizability in visible images, not only in low resolution images, but also in high resolution images. And also there can be a challenge for algorithms also, or in general for a scientific point of view, like when planning or defining some transverse for future missions. And so something that adds some outcome, and not only by computer science point of view, but also from a planetary science point of view. And so we decided to go with boulders and craters because are probably the most common features not only on Earth, but also in the whole solar system and probably elsewhere, because craters are simply impact morphologies that really are found on Earth, even if are bigger than usual and are less because our atmosphere protects us. But also in every image of the moon, you can recognize craters. While if you took photos with your mobile phone or with a telescope. While boulders are typically piece of rock, so you can recognize and also familiarize with them because you know already on Earth how those are and what are the possible problematics that they cause, for example, when planning a potential traverse for an unmanned robot. And so we decided to choose those two single features, craters and boulders. But then we decided to go a step further and try to find an additional challenge that is kind of on top of the detection of those craters and boulders that can be defined as a potential hazard for a mission that could be easily be performed by automatic rover or a manned rover. And we decided to create something that is similarly and usually is done while performing rover mission. And this the path, automatic path or manual path design, like where do you want to go to take some scientific samples, or where do you want to go to explore new places? And usually this problem, the path design is usually a common problematic because it's not only on Earth, but also not only on other planets, but also on Earth. For example, let's imagine Google Maps. When you say find the best route between 2 points, this is a common path design problem in which the algorithms takes the best route, taking into account several aspects like traffic, distance, speed, or way, like the method that you're using by foot, car, public transport system. And so this challenge is really similar, but we then thought about the complexity, because doing such complex task with automatic or machine learning algorithms is not really easy, because it will require a lot more of data to be trained off. You need to be more precise in assigning the weights that the algorithm will learn during the training itself. And also, it's not really that much easy to build something automated that takes into account not only like visible images, but also, for example, derived data like the slope derived from a digital elevation model, and so on. And these may restrict the accessibility of this challenge only to a specific computer scientists or planetary scientists groups and teams. And so we decided to take a step back and try to generalize this challenge by having this approach made by manual thinking, manual processing, instead of relying only on machine learning. Participants will have the freedom to go through machine learning, but at least we require something prepared manually. And so this is also connect with the public and the classroom challenge, in which all the participants have the freedom to choose whether they want to go, which approach they want to use, and then we evaluate how they decided why they decided to go with that approach instead of another, and why, for example, they decided to go into a specific place rather than in another one. Because we also asked the participant to go through several points of interest that can simulate, or at least they're trying to simulate, scientific outcome places. For example, a place where took a sample or a panorama or hyperspectral sampling, and so on. And so then we faced another problem: which dataset we needed to use, because there are a lot of data. There are thousands of terabytes of data available from orbiters, especially on the moon. And we have very high resolution images. We have hyperspectral data. We have derived products like digital elevation models. We have thermal data and many more. But then again, we needed to think about not only from a geological or a scientific point of view, but also from a general point of view, which may be the point of view of scientists in computer science, or people that are only enthusiasts of machine learning, and or in astronomics and geological sciences, but they don't have really a background in data processing, for example, because most of the data, especially in spatial, extraterrestrial data, like from the moon or Mars and so on, usually the datasets are free, but in most cases you have to process by yourself. And this is another thing, a point that we needed to figure it out: which data we want to provide to the participant, which is the best format to be compatible with at least most of the framework that there are, machine learning framework or GIS softwares or other kind of images, because there are, for example, hyperspectral cubes that needed specific tools to be opened, or raw images needed to be further processed. And so those are all steps and problematics that we had to solve before launching, or at least to better define this data challenge. Because then, at least at the end, we had this kind of huge data set with high resolution images, but were thousands of gigabytes, and we cannot ask the participant to have high computing, high power computers to process that, but also for sharing, because not everyone has access to network bandwidth very high, and so on. And so we decided to downscale the images, provide and find a good balance between resolution and weight of the files, but also change and find a specific format, like, for example, GeoTIFF, that is lightweight, or at least mostly lightweight, compatible with most of the framework or Python or computer in general, all the programming languages, but also with PowerPoint and other common used tools. And so at the end, we'll now leave the speak to Javier, because the last problem was where now what do we want to place this data challenge? Because now we have what is a data challenge? So what do we want to do? Which are the targets? Which are the possible participants? But then we need to choose a place where to perform this challenge. And Javier, that really helped us to define better the region of interest, will probably speak better than me about this the choice that we made. So please, Javier, join us.
Okay, thank you, Giacomo. Yes, so when we were thinking about the region to take out the challenge, we have to remember that Explore is focused on exploration. So this is one of the main point of what we're trying to do. So we try to look for a place that could be realistically interesting for human exploration or robotic exploration in the future. So in this sense, we wanted to focus in geological heterogeneity. This is really important because the moon is a place that is not really so variable in the surface that it has, but there are some places that can be kind of interesting, and Architas Dome is one of them. So Architas Dome is located inside the Mar Frigorifis. It is located at 55 degrees north and 0.9 degrees east. It is an interesting location because the domes are located inside the Mar, so it's a basaltic flow cover that we have in this place. But to the south, we have a different kind of surface. So we have a more older, more rugged surface that correspond to the rim of the Procellanum basin. So this dichotomy is really interesting, as we can see in the geological map to the left of the image. We see that we have at least 4 different big geological units. So we have the highlands, we have the Mar, we have a rill that is kind of a deep valley in the middle of the location. And then we have the Architas Dome on top. You can see them as a purple ring in top. So basically, the idea was to have this kind of variability because, as I was saying, it can be a potential or a possible real mission of an interesting place to properly explore. So as Giacomo was telling us in the prior example, we can see that this place has a lot of craters and boulders. These features are more or less typical to all the lunar surface, and this is not the section. But we can also see variability on these features. We see older craters with more eroded rims, but we also see fresher craters that are more recognizable because we see brighter spots that can be seen in the image. So with all this combined, we ended up with one image of the Lunar Reconnaissance Orbiter, the narrow angle camera, one image that covers all the place. And we also have digital elevation models that the participants can use for the next steps of the challenge. Another thing that we did in this region was to select interesting or possible interesting points for a scientific exploration. As I was telling you before, the idea is that we're trying to simulate an exploratory mission. So we also selected some specific sites that could be interesting to visit scientifically. So the participants have to use the craters and the boulders that they recognize it via the machine learning, and they have to take all this together and try to reach these interesting points that we were talking about. We can go to the next slide. Okay, so Once we had the region selected, we kind of decided which were the steps that we want the participants to follow. As Giacomo was telling, initially our idea was more like a full machine learning experience, but as we were seeing the kind of the complications and to make the challenge more open to all people, we decided to also implement like a little let's say human evaluation, human exploration part. So in this regard, we created, or we divided the challenge in 3 steps that we can see here. We have a first step that is a more machine learning heavy task, that is of course the preparation of a machine learning model that would be able to evaluate and classify different images of craters and boulders. This first step is going to be qualified using confusion matrix, precision, recall, maps, the amount of future detected, and all these kind of more qualitative measures that we can do to the performance of a machine learning algorithm. So this is going to be the first step. In the second step, the participants will have to use the model that they trained in the Architas region. So the prior step is more general. We selected a lot of labels, we retrieved a lot of labels from another images and existing databases. So in the step 2, they will have to use the model to detect these same features in the Architas region. The end goal is that in this step, they will generate a kind of they will end up with a number of detections that we can compare with a human-made map that we made to see the accuracy of the detection, if they are real detections, if they have proper shapes, if the distribution in general is similar to what the human can do. So we can have this point of comparison between the machine learning algorithm and a real, human-made map of the same region. And at last, we have the step 3, that this is going to be more or less similar to the classroom and the public data challenge, but of course with more complexity behind. That will be the definition of a traverse in the Architas region, of course taking in consideration the prior detections of craters and boulders. So the traverse can be able to manage to avoid this kind of difficult regions. We also selected a few another kind of constraints. For example, we only allowed a certain kilometer length traverse, and we also put some constraints in the slope of the region. That is why we are also providing the DEM. So the idea is that at the end, the participants will have to integrate all the information. They will have to use the results of their models. They will have to use the data that we're giving. And of course, they will have to compute the better traverse using all the information and the scientific points that we were collecting for the Architas zone. So this is more or less the steps that we decided to follow. And yeah, I think that is it for this site.
Thank you, Javier. And yeah, we'll just add that this QR code, if you want to scan it, it will just send you to the explore-data-challenge.space website. And if you have any question, you can join us, write us, and yeah, that's it.
Brilliant. Okay, well, thank you very much, Giacomo, Javier, Nick, and Dan, and also Ingo too. Does anybody have any questions? I think we also just generally had some discussion points. I mean, I think one of the things that really comes through is complexity of defining the challenge itself, and the data sets, and defining the evaluation system as well. I was looking at the aerial data challenges site today and seeing that you've been having some problems about defining almost perfect scores, and separating those out a little bit. Ingo.
Yes, absolutely. I mean, people do try to hack your challenge, whichever way they deem possible, and you have to. Most of the things you can anticipate and guard against, but sometimes, especially if you're comparing probability distributions with a distance metric, it becomes a little difficult. Yeah, it's quite an evolved process to set this up, and to benchmark all of that stuff, and quite often you get it right. Sometimes there are things that you need to update, which is pretty normal for a data challenge. But yeah, if it's the one thing we learned, once you launch it, it's not the end of it. Participants don't just like go and do it, but it's, you're building a community. So we've got a Slack channel, we've got an email list, we've got, regular telecons with people, so people have questions and so on and so forth. And that is really, really nice and rewarding when people really like engage with your science, but it's something that needs to be taken into account when organizing that it's quite a long journey.
And have you had much in terms of, do you get much in terms of repeat participation? Do you get the same teams joining each year, or is it? Actually,
yes. Well, it's sometimes hard to tell because people can just choose whatever username and be anonymous, but from the email addresses and the usernames that people have chosen, there are quite a few repeat people, which is nice, including people from industry and a mix between machine learning academics and astrophysicists. So it's people seem to like it, so they do come back, which is great.
Brilliant. Good. Again, if people have questions, then please do drop it in the chat, or put up your hand, or put it in the Q&A. Nick, I mean, what's your experience, or how do you feel about your experience? And Giacomo, well, this is really a question for all of the Explore team. How do you feel about your experience in trying to launch Challenge for the first time?
So it was, as Giacomo's title mentioned, it was a challenge within the challenge, right? And we were too ambitious, I think, in the beginning, trying to make it too complicated challenge and not have a clear definition or a clear question that you can ask in one sentence. Basically, if you need 10 minutes to explain what your challenge is about, then it might not be exactly well defined enough. I don't know if you want to add anything to that, Giacomo.
Yeah, indeed, it was a challenge within a challenge, because when at least for me, but also I think for Dan, Nick, and Javier, it was the first time organizing a lunar data challenge or a data challenge in this field, especially using machine learning. So there's a lot of things, because commonly you heard a lot about machine learning, and you think about that is really an easy task to do. Yeah, you can use machine learning and do stuff like a computer that can do everything that you want. You can just ask it. But actually, behind even a single machine learning problem, there is a lot. But it is not only from a mathematical point of view or informatic point of view, but there is a lot of organizational stuff about where to store the data, which data, of course, what are the targets, what are the evaluation methods, how to avoid, for example, to mix a hackathon with a data challenge in which they try to solve the challenge by hacking the challenge and not properly doing some challenge. And so all of those things needed to be taken into account. And initially we started with, we can do this data challenge by using machine learning, detecting things, programming a rover that just go around by itself, detecting things and so on. But then we kind of faced a wall that was our also, at least mine, limit about the comprehension of machine learning. So we needed to figure it out, a good compromise between the challenge and the feasible challenge, in which we needed also to, for example, and then in this will for sure talks better, how to make it more feasible for students that are not even in higher grade of education, like pupils from 10 to 14 years old. How do you explain in easy terms what is machine learning and how it can improve their knowledge, for example, in specific fields? And so, yeah, it was a challenge indeed.
I think, Giacomo, that was a key point in, I think, in our process when we split between, let's say, a more expert researcher-based challenge and a more junior public challenge, because we were trying to mix them too much together at one point, and I think separating them helped us a lot in being clear to both communities.
Yeah, we wanted to have them be separate challenges, but for the people taking part in the what is now the classroom and public challenges, we wanted them to be able to see what actual research was being conducted in the machine learning challenge as well, and to be able to see, like, oh, these topics that I've just learned about, that these researchers, these students, academics, professionals are now actually using these topics in a like real life sort of use case. But yeah, we were sort of trying to blend things too much that it was getting difficult to define one or the other. But yeah, I think we got there in the end.
Okay, thank you. We have a question actually from Luca Montebon, who would like to know, are you available to collaborate building up data challenges with machine learning on other topics? Luca, actually, you are able to talk, so maybe you would just like to say a little bit about what it is you have in mind. Are you able to unmute? There we go. We can't hear you. Let me try and promote you to panelist. Luca, can you hear us? Or are you able to talk? No. Okay.
Can you hear me now?
Yes, I can hear you now.
Oh, okay. Sorry, it was a problem just to try to connect with the voice. Yeah, no, my question was if one has a possible topic that could be explored with machine learning and with a data challenge, is it something that can be built up together? Because, you know, I know very little, almost nothing about machine learning, and you have accumulated such an experience about setting up a big data challenge. So I might have a topic, but I don't have the expertise that you have. So is it something that can be worked out together? Thank you.
Yeah, I think probably yes. Depends, of course, about the topic, because at least my experience with machine learning is kind of limited, especially in image processing and object detection and segmentation. But even in this field, it's pretty limited. So I don't have, for example, from my side, a vast experience in all machine learning techniques, especially with other kind of data, like, for example, hyperspectra and so on. But we definitely can figure it out if it is possible and compatible with our knowledge, of course, but definitely, yeah.
Because so just to follow up, basically, as I understand this explore data challenge, is it one-off, or is it thought to be, you know, a project that involves other topics in the future and becomes like a Zooniverse, you know, that a few years ago that this idea of citizen science was developed at Oxford, for example, and became like a Zooniverse with many projects and a dedicated platform. Is it supposed to become something similar?
Well, as for now, it's kind of our idea is to replicate this data challenge even the next year, but it depends also how it will go, of course, this year, and especially since the Explore project is not unlimited project, it should end like the end of the next year, if I remember well, more or less. So all the things that we are developing are intended to be also taken by the community, or it is a desirable target that the community at a certain point can take over. For example, if the Explore project is not funded or anymore, is not renovated, or other projects can take over, if the community can kind of take over, even us as a community, not as a project members, can take over and build up again, that will be definitely done. We kind of thought about also converting the data challenge in a proper Zooniverse challenge, but we ended up into straightforward data challenge because we didn't know exactly how to build up everything, and so to reduce a bit the complexity, we just stepped off and did a normal challenge. But yeah, definitely we can do something about collaborating and creating more data challenges.
Ingo.
Yeah, just to add to that, I think it is possible to have a sort of generic platform for this, and I think what you should probably look into is some of the Kaggle challenges, because that is, you know, the standard platform for these challenges across machine learning generally. We've written our own. What you need is a website and a proper backend, server backend. This is, once you've got that, you're sorted. You can run whatever you want on it. Really, it becomes a more traditional organizational project. Of course, you need your data set as well, but once you've got that, it's fine. And a lot of the data challenges at ICML, NeurIPS, ECML, and so forth, and ICLR, they all use off-the-shelf challenge websites. So there are platforms that you can use. They're pretty good. We didn't go for them in the end. I think possibly next year we'll do that because they've been bug tested to the extreme. So you can get off-the-shelf components, and through Kaggle you can actually host stuff, because that's an off-the-shelf hosting platform. In the UK, we're working towards something additional to that. So through the Alan Turing Institute, which is in the UK, it's the Machine Learning AI Institute. We're working on building a space science interest group, through which we can then host or provide a platform for hackathons and these challenges as well. But we only just got the interest group accepted, so this is a bit in the future. But yeah, it is. If you have an idea and you want to do this, it is definitely possible, and the tools are out there. We can have a chat offline if you want, but it's go for it. It's fun. I recommend it.
If I can add to that, Anita and Ingo, what I think the underlying question a bit here is also how do we keep our experience and knowledge from getting lost? So we have some experience. Ingo, you have a lot of experience. It's probably mostly inside your head. So how can we create a platform or community or some place where all this experience can be joined by the communities, the Astro and Planetary science communities, to easily start these kind of new challenges, because I see again that if Luca is starting this kind of challenge, he has to start all over. He has to fall in the same pits as we have, and that's not very efficient. So if you have a way to somehow keep this alive and share our experiences or expertise, or have some kind of community on that. I have no idea how that should be shaped or what's the structure of that, but that would be we would have liked that to be there.
Ingo,
sorry, yeah.
Sorry, you had your hand up.
I fully agree, and I think we're very early on, and I think there needs to be a community building exercise. It'd be ideal if we have workshops on this, for example, because it's lessons learned is a lot of pain avoided, and so it's machine learning in astronomy and planetary science is still pretty young, and it was really nice to see that at ICML we for the first time had a workshop on astronomy and ML, and it was very well attended. But it's a very small but burgeoning community, and I think something like, for example, Europlanet or EPSC might be a very good, for the planetary science domain, a very good platform to do that. Where we literally every year the EPSC sit down, this is what we learned, do you want help, sort of thing, bit of a workshop. It's just an idea, but
absolutely. I mean, I think this is something that Europlanet is really interested in, and we've sort of seen how the aerial one has grown and what interest there is out there. We're trying to support Explore in launching a lunar one, but I think that there is interest, there is an opportunity, and from a Europlanet perspective, where one of our main sort of reasons of being is to foster collaboration and interdisciplinary collaboration between different sectors. This seems like a really important thing that we should be doing, and it seems to be a place where we can have a function beyond EPSC and in providing a sort of platform or a grouping to support this. I know we keep saying this, but we have some tools that we're starting to sort of roll out for membership, things like a community Slack, where hopefully we can start to create some conversations around this. We also next year have our Europlanet Research Infrastructures meeting. We don't have, or at least EPSC next year is going to be joined with the DPS in the States. So as we would still like to have some kind of forum for the European community to meet in a slightly different format, we're looking at having a workshop-based meeting in June in Bratislava, and maybe actually having a meeting or a workshop, a hybrid workshop about data challenges for planetary or astronomy. Then actually maybe that's an opportunity to do that, or to have a discussion about that. But I mean, certainly we are very supportive about it. We, this webinar, we can record that, we can share that, and sort of hopefully make at least some of these experiences and case studies available, and kind of highlight them to people that are thinking about it in the future. But I mean, I definitely think that if you have ideas for things that you would like to do beyond that, then we would be very supportive in trying to find ways of sharing that knowledge, and making those connections. I mean, there are other people within the planetary community like RAMP and so on that we've had sort of some discussions with, so that there's other people not on this call today that are definitely interested in this kind of thing, and if we can sort of start to grow a community in planetary science, but also crossing over to other areas of astronomy, then that would be great. Okay, we are over time, so thank you ever so much to everybody that participated today. Particularly thank you, Ingo, Nick, Giacomo, Javier, Dan, for participating, and Luca for joining the discussion, and everybody else that that joined the call. And yes, hopefully this will be an ongoing discussion and something that we can support with via Europlanet. So thank you. The next webinar will be on the 25th of October. It will be about mentoring. The mentoring program supported by Europlanet, but also some case studies of that and other programs. So please do join us then. And thank you very much.